Hi everyone. So far in our work with limits, we've been estimating the value of limits given a graph or a table. And today is really where we're going to make the shift from estimating the value of limits to calculating them exactly. So when you're thinking in terms of where we're at in the unit, this is going to line up with sections 1.5 and 1.6. So remember, if you look back on page 1 in the packet, you can read through what are the targets that we're going to be responsible for in these sections. So we'll make sure to go through those when we're back in class, but it would be worth it to take a look through there and see what we're going to be responsible for in this section. So, to get us going here, we actually didn't do this investigation. But here's a big idea when it comes to finding the value of a limit exactly. So if we evaluate f of a, so a is some specific value. So if we evaluate a function f at a specific value of a, and that function value is a real number, so in other words, there's no undefined values, and we're not looking at a piecewise function where a is the breaking point, then the big idea is the limit as x approaches a of f of x is just f of a. So really what we're saying is if we want to calculate the value of a limit exactly and we're given the function, we're just going to plug in the value. And that's going to give us the value of the limit. So here's what we mean by that. In example number 1, we're looking at the limit as x approaches 5 of x squared minus 4x plus 3. So what we're going to do is just take this value of x, we're looking at x approaches 5, and we're going to just plug that in everywhere we see x. So to calculate it, we're just going to have 5 squared minus 4 times 5 plus 3. We're going to simplify that. 25 minus 20 is 5 plus 3 is going to give us a limit value of 8. So because when we plugged that value into the function, we did not get an undefined value, the value that came out is the value of the limit itself. So our first goal is always just going to be to plug in that value of x to find the limit. So the next two examples operate the same way, so we'll leave those out, and we can always address them if you have questions when we're back in class. Now, we have to be a little careful if we actually are working with a piecewise function. So when we're working with piecewise functions, if we're just trying to find a one-sided limit, we're going to try substituting the x value into the appropriate side of the breaking point. If we're working with a two-sided limit, we're going to check both sides of that breaking point, but that's only going to be important when the x value we're looking at is the value of the breaking point itself. So let's look at a couple examples to really understand what that means. The first thing I want us all to be aware of and really clear on is when we're talking about this breaking point, we're talking about this value here. That's going to be our breaking point. So what kind of splits up the pieces of our graph? That's what we're referring to by the breaking point. So for our first example here, we want to look at -2 from the left. So if I'm looking at -2 from the left, that means I really want values that are less than -2. So that tells me for this problem, I care about this piece of the graph, where x is less than -2. So I'm going to use that first piece and plug in -2 wherever I see x. So I have the opposite of -2 squared minus 8 times -2 minus 15. And then simplifying that, -2 squared is 4. The opposite of that is -4 plus 16 minus 15. And that's going to give us a limit value of -3. Now, in our second example, now I'm looking at -2 from the right. So really I want to consider x values that are greater than -2, because I know everything to the right is going to be greater. that tells me I should just be looking at this side of the function. So in this case, we're going to use this piece, and we're going to still substitute -2. So I have -2 times a -2 minus 6, which is 4 minus 6, and our limit value is -2. So now when I go to consider the two-sided limit, right, just like before, I have to compare the left side and the right side. Since in this case those do not agree, just like before, we would say this limit does not exist because the limit as x approaches -2 from the left of f of x is not equal to the limit as x approaches -2 from the right of f of x. No difference here in how we justify our answers. Now, for this last one, this is really what this point here was getting to about two-sided limits. So in this case, at x equals -2, I had to check both sides of the limit, both one-sided limits, because -2 was that breaking point. However, when I look here, I'm looking at the limit as x approaches -3 of f of x. -3 is not a breaking point. I know -3 is going to be less than -2, so the only piece I care about is the first piece of my piecewise function here, which is defined for x is less than -2. So I don't need to worry about a two-sided limit because this is the only piece of the function that defines, or that's defined for that value. So in this case, I'm just going to consider the first piece, and I'm going to plug in my value of -3. And then simplify to find that value. So -24, -9 plus 24 is 15, minus 15 gives us a limit of 0. Okay, so those are kind of the more basic examples of how we're going to find exact values of limits algebraically. Now, there are going to be some times where those methods aren't quite enough. So, for example, let's look at option number 1. If I try to plug in -2 into my function, in the denominator I'll get -2 plus 2, which is 0, which would give me an undefined value. So that tells me I have to do something first. So I'm going to take my function kind of off to the bottom here, and I notice that I could easily factor my numerator. I have a difference of squares, so I know that's going to factor into x minus 2 times x plus 2 over x plus 2. Since it has a factor in common between the numerator and denominator, I can go ahead and cancel that, and I get a simpler function, which is x minus 2. The nice thing is now I know that the limit as x approaches -2 of my original function, that's just equal to the limit as x approaches -2 of my simpler function, which is just x minus 2. These two functions have the same limit value. So now I can go ahead and just substitute. That's not going to cause me any problems. I'm going to substitute -2 for x, so I'm going to get -2 minus 2, which is -4, and I've got my limit value. Another scenario might look like number 2. And number 2, again, I can't just substitute because the square root of 1 is 1 minus 1 is 0. I have a 0 in my denominator, which would give me an undefined value. So I've got to do some algebra to manipulate this. So in this case, I'm going to focus on my denominator here. And I'm going to go ahead and multiply by the conjugate of that denominator. Now, it happens to be that in this case I'm multiplying by the conjugate of the denominator. We'll look at examples later where it could be in the numerator, but the process is the same. So on both the top and bottom, I'm going to multiply by the conjugate. Right? It looks the same, except you'll notice where there was a minus here, it's a plus in the conjugate. So now the top, I'm not going to distribute that at all. I'm going to leave it as it is. So x minus 1 times the square root of x plus 1. Now, in my denominator, I am going to go ahead and distribute. So I'm going to multiply the square root of x times the square root of x, which is going to give me x. I've got the square root of x times a positive 1, which is going to give me plus a square root of x. I'm going to have minus 1 times the square root of x, which is minus square root of x. And then negative 1 times a positive 1 gives me a minus 1. And here's why this is really helpful. My square root of x's are going to cancel. So my numerator hasn't changed. But on the bottom, all I'm left with is x minus 1. Now I can cancel that factor of x minus 1 from the top and the bottom, and this simplifies really nicely to the square root of x plus 1. So now that I've done all this algebra, I can go back to my limit work. My limit as x approaches 1 of the original function is going to be equal to the limit as x approaches 1 of my simplified function. And now I'm going to substitute as usual. It's going to be square root of 1 plus 1, which is going to give me a limit value of 2. All right, the last type of example we might encounter is something that looks like this, a complex fraction. This says try eliminating denominators. I think of it as killing off the fraction because I don't like having all these complex fractions. So again, I'm going to take my algebra down here and do some work. Now what I notice here is I have these denominators of x minus 1 up top and bottom. I want to get rid of those, so I'm going to multiply the top and bottom by that denominator. And here's why I'm going to do this. I'm going to distribute this x minus 1 to both terms from my original fraction. When I multiply 1 over x minus 1 times x minus 1, those are going to cancel and I'm just going to get 1. Now, when I multiply x minus 1 times a negative 1, I'm going to get a negative x minus 1. On the bottom, I have 1 over x minus 1 times x minus 1. Those are going to cancel, and I'm just going to get 1. So now I'm going to go ahead and distribute this negative. So what I'm going to get is 1 minus x plus 1. Since that was over 1, I'm just going to leave that out. And now I'm going to simplify it, which just leaves me with 2 minus x. So that whole nasty complex fraction just simplified to 2 minus x. So now I know that the limit of my original problem is just the same as the limit as x approaches 1 of 2 minus x. I substitute 1 for the x to get 2 minus 1, and my limit value is 1. So a lot of the practice we do when we're back in class will be focused on working through these algebraic procedures. So there's one last piece of this, which is just learning some properties of limits. And I'll warn you, this is going to be a lot of writing, but the basic principle is pretty simple. So we have properties of limits. So suppose we have two functions, f of x and g of x. I know the limit as x approaches a of f of x is L1, and the limit as x approaches a of g of x is L2. Given that information, we can use properties of limits to evaluate some more general limits. So here's what I mean. Here I have the limit of a sum, right? So we have the limit as x approaches a of a sum of functions. There's a property that tells us the limit of the sum is just equal to the sum of the limits. So in other words, this is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So now I can use the given information. I knew the limit as x approaches a of f of x was L1. The limit as x approaches a of g of x was L2. So that limit is just L1 plus L2. So the property tells us that the limit of a sum is just the sum of the limits. And that type of logic is going to follow through for all of these properties. So in this case, we have a limit of differences. The property tells us that's the same as the difference of the limits. So now I can rewrite this as the limit as x approaches a of f of x minus the limit as x approaches a of g of x. And using our given information, I know that's just equal to L1 minus L2. Okay, so we're going to use those same ideas to fill out this chart. I probably won't read the whole thing as I'm writing, but I do want you to copy down these properties. So I have a limit of a product is equal to the product of the limits. So that limit is going to be L1 times L2. The limit of a quotient is equal to the quotient of the limits. So that's going to be L1 over L2, assuming that L2 is not equal to 0. Now we're going to have the limit of the nth root is just equal to the nth root of the limit of that function. Whoops, we're just going to leave it as that. And then last but not least, if I have the limit as x approaches a of k, which is just going to represent a constant, times our function, then we can move that k out front. So we have k times the limit as x approaches a of f of x, which is just going to be k times L1. Sorry, let me back up for a minute. Up here we should have put, we know this limit as x approaches a of f of x is L1, so this would be the nth root of L1. So that's how those properties work. So I'll just show you one example, and then again we'll leave an example to use in class if needed. So here's how the problems will actually look on an assessment. So given that the limit as x approaches 8 of f of x is negative 9, the limit as x approaches 8 of g of x is equal to 2, and the limit as x approaches 8 of h of x is 4, they want us to use limit properties to compute these limits. So here's where we could show, now here I'm going to show all the steps, and then I'll show you what work I would expect you to write. So the first property I see here is that I have a limit of differences. And I know that's equal to the difference of the limits. So I could write the limit as x approaches 8 of 2 times f of x minus the limit as x approaches 8 of 12 times h of x. Now I notice I have, like we called here k was this constant, I have some constants here. And what my properties told me is that I could move those constants out front. So now I could rewrite this as 2 times the limit as x approaches 8 of f of x, not equals, sorry, minus 12 times the limit as x approaches 8 of h of x. So now I know these values. The limit as x approaches 8 of f of x is just negative 9. So I can do 2 times negative 9 minus 12 times, let's see, the limit as x approaches 8 of h of x was equal to 4. So I have minus 12 times 4. And now I can just simplify to find the value. So I have negative 18 minus 48, which is going to be negative 66. Oops, I'm sorry, I ran off there. So now I showed you all this work just to show you how we use those properties. However, on a test, all I'd really want to see is this work here. And the reason I asked you to show this step is because if for some reason you do the arithmetic wrong, I want to still be able to see that you applied the property correctly to be able to give you some partial credit. So I know that was a relatively long video. Thank you for taking detailed notes and hanging in there. We will get lots of practice on this when we are back in class, so I will see you then. Thanks.